Hello everyone, welcome back to my YouTube channel. And in this video we are going to learn about special character normalizations with Japanese as an example. These things can be used for other special characters such as Chinese characters or Korean characters or any special characters that access in Unicode, right? So this is the study case. I have word apato, right? Apato. So there is a line mark above the A. It means that you have to spell it a little bit long. Apato. So it means apartment, right? And in Japan, there are three ways of writing apartment so far, as I know so far, right? So these are the three ways. So the first one is called full width kana, right? This is the normal one, or this is common way people writing katakana like this, full width, or in Japan they call it hankaku. Sometimes it calls 2 byte characters like this, which is half width kana or zenkaku, or 1 byte characters. If you see the shape, it's the same, but the width is kind of like half of it. And actually, the Unicode is different. And the third one is not common, but it exists for certain use case. This is called square symbol, right? This is the apartment square symbols. So the study case is, imagine that if you need to write software where you have to match between your data. Let's say your data is apartment in katakana, in normal one, but the input can be like the first one, the second one, and the third one. So how your system able to understand that basically it's basically the same meanings apartment. To do that, we have to normalize this kana with Unicode Normalization forms algorithm. This is a way to determine whether any two Unicode strings are equivalent to each other. And to do this, we are going to explore about 2 types of convergence: canonical equivalence and compatibility equivalence, and also 2 types of directions: decompositions and compositions. So we have to find equivalency of the two strings, right? So canonical equivalence means that characters which represents the same abstract characters and which when correctly displayed should always have, so this is the keyword, the same visual appearance and behaviors. So when you have two Unicode strings and then you correctly display them, they should have the same appearance and behavior. For example, I have kana of pa, right? Pa, and that is the Unicode. And if we do canonical equivalence conversions, it becomes 2 characters, because if you see closely, it's basically combination of 2 characters. The first one is kana ha, and the second one is like the voicing symbol that make ha kana change to pa. And this is bidirectional, so you can uh, sorry so you can convert from the left to the right, and you can convert from the right to the left. And if you see that they have the same appearance if you combine it and behavior, even though on the right they technically different Unicode, right? You can see they are different Unicode. So this is also called combining sequence subtype. So there are several different subtypes of canonical equivalence. If you want to see all of them, you can check with the link I've given in the bottom left of presentation or in the video descriptions. Next, we are going to check about compatibility equivalence. So basically, it kind of opposite with previous one, which is characters which represent the same abstract characters and which may have, this is the keyword, distinct visual appearance or behavior. So the appearance will be kind of different, right? So this is the example. This is kana of A, but half width, and that's the Unicode. So if we apply compatibility equivalence, this become full width kana, right? So the visual appearance is different. The first one is just half width, and the second one is full width. And this subtypes is also called width variance. Another options is this. So this is the square symbol of apartment. And if we apply compatibility equivalence, this become, yeah, apartment in full size in a normal way. They looks different appearance, right? So this called square character subtypes. And again, if you want to check another subtypes, you can use the link in the slide or in the video description. So we have canonical equivalence, which is the same appearance. And then we have compatibility equivalence, which is distinct visual appearance, right? So let's check about, before we check, if you see that the line is only one way, right? One way. So it's not both way. We cannot switch from the right to the left. So about directions. Now we have two directions. The first one is decompositions. It means break characters down, right? As easy like that. We have seen this example before. So we have pa and then break down into two characters like that, right? And then we have compositions, which is the opposite of decompositions. Merge separate characters into a single Unicode characters. So from these two characters become one characters, right? This easy to understand, right? So we have four way to change, manipulate the characters. Now Unicode normalization forms basically is a mix match, right, of these four transformations and directions, right? So I have a table here. So the first normalization forms is normalization form D, or NFD for short. So basically it is canonical decomposition. So we apply canonical conversions and decompositions. Yeah, we are going to see the example after this, okay? The second one is normalization form C, or NFC. It is canonical decomposition And then after that, we apply canonical compositions. The third one is normalization form KD or NFKD, right? K here means compatibility. So it means that we apply compatibility conversions and decompositions. And the fourth one is normalization form KC or NFKC. It is compatibility decompositions. And after that, we apply canonical conversions and compositions. So the first one is NFD or normalization form D. Basically, we apply canonical conversion and decompositions. So as example here, I have kana, and then we apply NFD. It becomes the ha and then the voicing symbol, right? As easy as that, right? It is a canonical conversion, and then we decompose it. So if we compare, this become true, right? What if we compare like this? So we normalize using NFD the ha and then voicing symbol, and then try to compare with pa. So the result is false, obviously. Why? Because we will apply canonical decomposition to a character that actually already decomposed, right? The second one is NFC or normalization form C. It is canonical decompositions, what we do in NFD, but after that we apply canonical compositions. So for example, we are going to use the same character. So this is the ha and then the voicing symbol. Right, we apply canonical decomposition, which will remain the same because it's already decomposed and it's already a single unique characters. But after that, we apply compositions and becomes a pa. And what if we have pa and then we apply NFC? So it becomes ha and then voicing symbols. After that, we apply canonical compositions and it becomes pa. Now let's take a look of NFKD or normalization form KD, which is basically we apply compatibility conversions. If you remember, it is a conversion that changes the visual, and we also do the decompositions. So if we have a half width kana of pa, and then we apply compatibility decompositions, so it becomes full width kana, and then we decompose, so it becomes two characters. What if we have the square shape of apartment like this? So we do compatibility conversions, it becomes the full katakana, if you remember, and then we decompose so that the pa becomes two characters like that. Okay, so that is NFKD. The last one is NFKC, right? It's not KFC, it is NFKC. It is normalization from KC, which is we apply compatibility decompositions like we did before in NFKD, but after that we do canonical compositions. So again, if we have half width kana, it becomes full width kana, but we decompose, so it becomes two characters. But after that, we apply canonical compositions, right? Which it merges the two characters become one character's pa. Another example, if we have the square shape apartments, we we apply the compatibility and then we decompose like that. And then after that, we apply canonical compositions. Basically, we merge into this katakana apartment. So let's compare the results of all algorithm. The first one is if we give the input that we want to normalize is the normal width or the full width of apartment. The number after that is represents the length of the string. Okay, so if we apply NFD, it becomes full width kana, but we decompose it so that the pa become 2 characters, right? Ha and then the voicing symbols, and then also the length of the strings become 15 instead of 12. NFC, basically we apply canonical compositions, so basically it will remain the same. Now NFKD, we apply the decompositions, right? But the conversions will remain the same because it's already a normal form of kana, but we decompose it. So it becomes like that and the length is 15. NFKC, right, is the same with NFKD, but we compose or we merge the characters. So it becomes like that, 12. The second row is if we input half with kana, right? As you can see, the NFD results will becomes the same as the input. If you see, the shape is the same, right? Why it's the same? If you think, right, we should decompose it, right? So actually, if you try it in your language, the half width kana of pa is actually 2 characters of Unicode, right? So if we decompose, it becomes the same because it's already 2 characters, right? So that's why if we apply an FD, the length also the same, the visual also the same. If we apply NFC, it also will be the same. But if we apply an NFKD, now the visual become different, right? Now becomes full width kana, but we decompose it because it turns into full width kana. Now we can decompose the pa into ha and voicing symbol, so the length will remain the same, right? And NFKC, so after doing the conversions, we compose or we merge the kana so it becomes shorter. That's why the length is smaller than the original input. So the third one is the square symbols, right? The length is only 3. NFKD and NFC will remain the same because we only do canonical conversions, right? It's not change the visual. That's why if we do decompose or composing, it will remain the same because it's the conversion is remain the same. But if we apply NFKD, the compatibility conversions, now it becomes the full kana and we decompose, so the length will become 15. And if we apply NFKC, it becomes 12 because we merge the katakana, right? So if you see this, which algorithm you think like overall, if you build a software, which one do you want to choose? Overall, like which one do you think is suitable for common cases? Right? I think it is NFKC. NFKC is the winner. right? Because it can translate into the normal katakana. So in your system, you just need to store the normal katakana, right? And then if you see regardless the input, you can always compare with the normal katakana. So this is the learning reference, right, that I use. And if you want to take a look how to do that conversion in Go, you can check the 4th links on this slide, right? So thank you for learning. That's it, what I want to share with you. If you are working in a company that have to deal with special characters, maybe someday you have to use this. Let's say if you are using search engine, if you're building search engine, then probably you will apply these kind of normalizations in your search engine. Or if you are validating text, probably you will also applying this algorithm in your systems, right? Until the next learning video, I hope you keep learning and stay healthy. I'll see you again. Bye bye.